Oye, ¿el almuerzo? Un poderoso de sangre. Tenía buena carne. Pero tenía a mí me dio comenzar a cargar, tenía una semillita de algo. Yo creo que sí, yo sí. Porque me comenzó a dar. Pero. Como era como jarilla, algo así de. ¿Tuviste que el restaurante, que la ermita era? Como tuviste que una vez te diste cuenta de una vez que digamos una que te comer y la verdad no estaba tan. Dijiste, tú como que hiciste un comentario y enseguida todo lo demás. Me está diciendo que por tú no puedes estar, a todo el mundo que corre está matando un HT un poco algo. Debe haber como la información de la página web que todo el mundo se quiera descarga, pero lo de ella están mandando. No, yo la acabo de mandar una HT porque comenzó con. Pero ¿cuál? ¿Cuál más hay de Guatemala? ¿Qué busca? Ah, la ambulancia. No, pero hace poco que eran ambulancias, una lancha marítima, pero hace poco nos pusieron. Ah, no. Ah, bueno, la unidad nacional de riesgo tomaste una ambulancia hace poco. Que nos mandaron una tabla para unas preguntas que recalamos, porque supuestamente como la semana es de los 50, ¿no te acuerdas? Ah, sí, pero nosotros. ¿Y por qué? Porque está en el presupuesto lejano. Que pedía un bote con una lancha como de 6 metros o de 9. De 9. Y nosotros, y el presupuesto decía otorgarse a menor cuantía de nosotros. Pero el de requerimiento de ellos no lo cumple ninguna lancha, ambulancia. No, y nosotros no damos tampoco. Es como una vez, me llamo una vez de la Universidad Nacional. De la Universidad de Nacional. Que están haciendo hecho de cosas. Entonces me dice que me manda un bote y yo le mandé a ver conmigo. Algo. Perdón, ¿a quién llamé? Ah, no, perdón, me equivoqué. Listo, yo estaba acá hablando y como que marqué. Le marqué el vídeo. Iba a mostrar en el WhatsApp. El de Guatemala. Y en otro la universidad. Manuela Montoya. Y yo cogí y le envié todo su poca pendejada. Yo cogí y le envié, mira, tengo este casco de casco, tengo. Entonces me dice, es posible hacerla entre 7.6 y 7. Y yo comienzo y llamándole. No, que voy a trabajar, estamos trabajando con un fondo que pasó para hacer una tesis. La universidad va a poner una plata, nosotros vamos a conseguir con una empresa y nosotros vamos a poner. Entonces yo le dije, y tú dices, no sabes que pasé un casco, aquella va a estar modificada. O sea, no le dije así, no, sino le dije, no, mira, nosotros no tenemos que estar cosas, vamos a perder tiempo. Esa vieja cuando uno demanda, cuando yo diga que el casco está costando como 200 millones de pesos. Sí, porque están acostumbrados a los frijoles esos que valen como 80, que no es. Sí. El solo casco, después ya viene el motor y ya con eso lo pueden andar. Oye, ahí el Fibergas, ahí es paisa. Ahí está la empresa de Fibergas que está ahí, baja por el pionero, bajando ahí, que se hace bote. Se hace bote hasta de 20 millones. Ese para una vaina. Oye, yo no estábamos ahí. Entonces, fíjate, Va bajando. Sí, afortunadamente sí. No aguanta. Mejor la beca, hasta el posgrado, la deuda del posgrado en ICT queda clavada por un poco de años. ¿Qué te parece? Y el chat sigo entrando por la página. Sí.
buenas tardes a todos. Saludamos nuevamente a los que continúan.
Good afternoon. Greetings to those of you who continue connected with us via www.colombiamar.co. We invite you to participate through our social media. We continue with the afternoon session using our two channels that we will enable to have access to the technical presentations that will run concurrently on design and production of ships. You can consult today's agenda via our webpage, www.colombiamar.co. On the page, we select go to the event. We will look at the event agenda and we pick the conference. If you like, you can select the language by selecting the option in the bottom button where you can choose either English or Spanish.
Buenas tardes.
Good afternoon. I am pleased to introduce the next presenter, Nicolás Ruiz Buendia. He's midshipman, and he will make a presentation from Cotecmar. He is a professional in naval engineering and naval sciences. He is a specialist in maintenance management. He has a master on hydrodynamics and mechanical engineering with an emphasis on advanced ship design. During his professional career, he has developed expertise in computational fluids, mechanics, naval architecture, mechanical design, and currently he works as a designer within the corporation. Today, he will talk to us about the estimation of the resistance to forward movement in shallow water with a low draft fluid, inland water ships. So the room is yours. Thank you, Captain. For me, it is a pleasure to present this paper was born from the managers of them, and it is the estimation of the resistance to the forward movement in shallow waters. It includes Nicolás Ruiz Buendia, Barat Berma, Luis Leal, and Mauricio Garcia Navarro, all of them engineers. The table of content will be the introduction and the operational need for the project, a process to define forms, that is how we arrive at the choice of how to build, an explanation of the numeric simulations that we worked on, a campaign of trial test or validation test, and lastly, conclusions. In introduction, it is important to highlight that Colombia has a maritime area of 928,000 square kilometers and a river extension of 24,725 kilometers. Now, what's the importance of this slide? Colombia's Navy has to be present and secure this vast expansion. So there was a need to develop a shallow water project for the purpose of maintaining the surveillance and control operations in hard to access locations, as are many of our rivers in Colombia. So these rivers fluctuate according to the rainy season or dry season, and due to this, the draft is reduced so as to make the river navigable by the Colombian Navy's ship. Now, this need was intended for secondary river, where the depth is as much as 0.6 meters. So the Western Operational Group was born, right? And there we have the Orinoco, the Meta, the Arauca, Guinea, all the Cotecmar for the purpose of solving this operational need and anticipating to the requirement of the Colombian Navy, we started designing a ship at the beginning of 2019, and we proposed 6 different models that met the operational requirements and we completed the design and with the design and construction of 8 low draft boats by the end of 2020. This was a significant challenge for COLOMBIAMAR from two standpoints, design and construction. Well, from the design office, we had to be completely sure that the boat met all the operational requirements. And to that end, we had to consider the particular theater of operation of the boat. Throughout its life cycle, the boat will operate in shallow waters with waters that are affected and then offer resistance to the forward movement. Another important aspect is that we changed the construction from fiberglass as it is traditional in these units, and we went to build the boats with aluminum. And this led us to improve our production processes. But not only did we do that, but we actually engaged in a transfer of technology with the crews, because we made it possible for them to train them and enable them to do the minor maintenance and repair the units, certifying them as welders, aluminum welders. Now for this, we did not, there was no object, no obstacles. We ran validation tests to be more certain of the complex challenge that lay ahead of us. And this prototype boat, we used to validate simulations to be that done and to make corrections and modifications to the design. Now, this is the operational requirement that was received by the Western Naval Force. It is a low draft fluvial combat boat, and what's innovating here? Normally, low draft boats would navigate in shallow waters are characterized by their lightweight, but the operational requirement was truly demanding. It was a boat with a capacity of 5 people, additionally a load capacity of 4 people for a total of 9, 400 kilograms of load, autonomy of 300 kilometers, which required enough fuel to be on board, and we had ballistic protection above the flotation line, which made it a boat no longer categorized as a light boat as these would be traditionally labeled, but actually we had a restriction in terms of design, and it was the power. Normally during the design, based on the speed that one might need to achieve, you calculate and you forecast the power to be installed to meet that requirement. Now we had a strong restriction, which is that the maximum installed power was 120 horsepower in a 2-engine configuration, each 60 horsepower engine. So we had these dimensions which were modified in the subsequent process. How did we run the numerical simulations? Well, we did them for 2 types of simulation, one in deep waters and another in shallow waters. So they have some significant differences to them, but also some common things. With the simulations, we solved the modeling of the turbulence. So we made the KOF STF for the time delta. We used a condition of time step up, which we applied in free surface. That is, these surfaces were monofluid, and we applied a restriction of delta and step up in free surface so that the number were less than 1. Now, the computational domain we defined based on the recommendations for IPC plane boats. Now, mesh we use two, one for deep water and another for multi-mesh for simulations in shallow water. I will explain them. These simulations were run in our server, which can be considered a high computational power server. We have 128 processors, 256 at 225 gigahertz, 512 giga of RAM, and in total it was 128,000 hours of computation without counting the optimization process. Now, all these simulations were done in actual scale. Now, with respect to simulations, I will explain the conditions, the borderline conditions. We imposed the fluid velocity in the negative part of the GXC. We imposed pressure outlet on the side. We used a sliding wall conditions for simulations in deep water. And in the y-axis, we applied a condition of symmetry. And that allowed us to reduce the computational domain, reduce the number of cells, and reduce the computation time. Now, with respect to the dimensions of the domain, we followed the recommendations of 7 length in the XY and in the Y7, and in the X axle, the depth. So to define the forms, we did hydrodynamic optimization. So we applied a semi-parametric variation on the initial hull, for which we obtained 300 variables to the design. What is it? Well, we take a hull that we can use as initial geometry, and we apply restrictions, modifications, minor modifications, not varying the nature of the design much. For this specific case, we applied the escalation in the 3 dimensions. Now, which restrictions did we add on this experiment? Minimum and maximum dimensions in the length, in the beam, and in the draft. Now, by restrictions, we meant the capacity of load, and the displacement was very high. So to reduce significantly the dimension forced us to have a very high draft, which was going to increase. So this optimization process was done for a speed of 15 knots. Now we can see here the difference in the forms. In blue, we see the initial hull, right? The prototype boat's hull. And in red, we see the forms of the optimized boat. In the end, we managed a reduction to the resistance of 7.5%, and we used the following length of 705, a beam of 3.42, displacement 3.72, and a draft of 0.33 centimeters. This forced us to have a boat with a very low keel to be able to meet this operational requirements. Now, with respect to the configuration of the mesh and the simulation, I previously mentioned that we use 2 techniques. One is overset mesh, and the other is working mesh. Now, in these sorts of ships, what happens? Well, they are subjected to drastic movement of pitch and rolling. So during the simulation, so how did we solve this problem? How did we move this movement through the simulation? Well, we applied initial trimming to all the simulations based on the speed that we wanted to analyze. To initially apply this trimming, we used the Savinsky series, which gives us a pretty useful series of trimming during early design phases. Now, for deep water simulation, we use the second mesh, and that creates 2 domains: the internal domain, which is the one that follows the movement of the boat throughout the simulation and generates an interpolation, a connection with the external domain to obtain the condition. Now, for these simulations, we used about 2.5 million cells. And for the shallow water, we could not use this manner of meshing due to the shallow depth. We ran the risk that the boat's movement would render this domain outside of the computational model. So we used the working mesh model which is deformed in one sector, and it is deformed in according to the movement of the boat. Also, in shallow water, you cannot overlook the viscosity effects. So you need to add a limit layer, which will represent the bottom of the boat and the river bottom. These will generate some viscosity effects, which are highly important when talking about shallow water. So we needed to apply the condition of a limit layer, and we could not impose it without sliding condition. Now, the simulations in shallow water were about 6 million cells for each simulation. How do we know when a boat is navigating in shallow water? Well, there is a way of describing it, which is by describing the surface waves. We know that waves are characterized by the amplitude, the height, the length of wave, the depth, and the period. And likewise, they have a number of waves, and it's K on the length of the wave. Now, from the standpoint of engineering, how do we know that a wave is of shallow water? Well, then we have two relations. When this depth on the length of the wave is less than 1/20, or when this number of waves that I mentioned before falls because of the depth is less than 10. So there we know that we are working in shallow water. And the equation of the speed of a surface wave, we describe it here as we can see it. What happens with this term tangent hyperbolic of two types, the depth over the length of the wave in shallow waters tends to be 0, for which we can assume that this term to the right is the same, is approximately the same as the depth over the length of the wave. And this allows us to define that the speed of a wave, surface wave, is the square root of the gravity times the depth. From this term out comes a figure that is very important, which is the depth flow number. As I said, this that is the relationship between the forward movement of the boat or the body being analyzed over the square root of the gravity times the depth. Now, what is the importance of this slide? In terms of the simulations and the behavior performance of boats in shallow water or ships in general, there are 3 regions: a critical region, a subcritical, critical, and a supercritical region. In these regions, different behaviors occur in terms of resistance to the forward movement. In the subcritical area, in depth of less than 0.7, these effects are not significant. And there is, from the standpoint of the design, a region that is very interesting, which needs to be studied, which is the critical. When you have the number of 0.7 to 1.2, where the resistance to the forward movement generates an impact. So there is significant resistance to the forward movement, and this is vitally important because that is what limits our being able to engage the boat in a proper speed. So after this supercritical region, you obtain a reduction in resistance to the forward movement. All this is theoretical, and it was proven in the simulations. Now, simulations were ran at 7 depths in shallow water, and they are commonly expressed as the depth where a ship is flowing in a relationship of the length. This means that when the relation is low, it means that the boat is navigating in deep water, and when it is high, it means that it is navigating in shallow water. Now, the power of the boat was really reduced, and a speed was very much at the limit of that prediction of resistance. Additionally, these marine infantry boats, as you can see in the graph, normally navigate in waters of 1 to 5 meters, which shows that this relationship of the length and the depth and the group number shows us that these boats are experimenting these effects of the shallow water. Over here we have the results of the resistance to forward movement simulation, and we can see that the results of the effect of resistance in shallow water which is the starting point for the design, were very similar to the maximum peaks of resistance obtained at a low depth. And the importance and the challenge of this design is here. See, because in every operational setting, when the boat is navigating in shallow water, this increase in resistance could not be too high, or that we would not have enough power to be able to overcome this peak and then achieve a contractile speed. In case that those 120 horses as installed would not have been able to overcome those resistance peaks, it is the difference between the boat getting to 15 knots or a little over, or stay below 7 or 8 knots according to the depth. Now, this would not be a significant problem when one does not have a limitation in power, because you guarantee that curve, that maximum peak of resistance will be overcome easily. But this was our main challenge and our main concern. Now, a way in which in the academy demonstrate this behavior of resistance forward movement is by graphic based on total resistance and the number of proof of depth. And here we can see that the biggest affectation occurred in depth number between 0.9 and 1, having a maximum peak in 0.95, which adds great value to our work, because the simulations were validated with what little theory exists. Actually, the state of art in shallow water, there's not that much. There are some studies, but for fast moving boats, Series 60, Series 62, but we didn't have hydrographical source, in shallow water, and much less validation campaigns, experimental validation campaigns as we did for this work. Now, this change in the resistance for forward movement does not happen with every component of resistance. We know that there's a viscous component and a residual component. The change in resistance to forward movement occurs in the residual component, but it is the component of greatest importance in resistance to the forward movement, accounting for about 90% of the resistance. In the viscous, you get a reduction, but it's not significant. How can we also validate our studies? Well, as I said, the theory and the state of the art in shallow water is not extensive, and experimental trials are very much limited. First, because they're costly, and second, because for a model basing to validate that it's somewhat hard. So experimental tests are limited to maybe 3 or 4 different depths. We analyzed a total of 8 depths, and we can show them in this graph, which is based on the length over depth relationship that I commented about, and also creating a ratio between the residual resistance in shallow water and residual resistance in deep water. Over here, we can see that the performance obtained was the same. Radovic and El Toro, who are the ones who have worked the most on this topic, resistance, the pattern was completely similar in the critical area, in the 0 to 9 to 1 in the depth number. Another aspect of interest and highly important for the Navy, for the Marines, is to understand the pattern of waves that is generated in shallow waters. Traditionally, we in naval architecture know about the Kelvin pattern, which is made up by divergent waves and transversal waves. This divergent wave is 19 degrees with 28 minutes, but this pattern only keeps a fluid number of 0.4. Now, what happens when we move above the 0.4? The pattern of waves is totally different. In the critical zone is where we must focus our interest and operational teaching to the pilots. Because in this condition, because of the definition of the fluid number that I showed you, the equation of it, we can determine that the speed of the boat over the speed of the wave is going to be the same. So in this fluid number, the wave follows the boat as if it were navigating with it. Now, what happens in this condition? You get a peak at the height of the wave, and therefore the energy of the wave. And this is vitally important because when a marine boat is navigating in this regimen, we normally navigate in riverside populations where you have small boats which could easily be affected by this energy of the wave. So we also generated, we transferred knowledge on the speed and the wave at which they should navigate to prevent these problems. If it's a speed below this critical fluid number or above, when this energy is reduced. Now, when this number exceeds 1.1, the wave pattern changes completely. You only see the divergent wave, and its angle is reduced drastically. In that condition, the speed of the boat or the body is so high that the pattern, the wave pattern, is not capable of following them. Lastly, we ran some validation tests, and the validation tests were not limited to speed tests. At the corporation, to validate this model, this design, to be certain of their performance, we did speed tests in operations areas, actual live operational area, maneuverability, tactical angle, longitudinal and transversal angle, which will be presented in a future article. But in this particular case, I will show the results of the experimental tests, speed tests. We did these tests in Cartagena. For those of you who don't know, Cartagena is a city in the department of Bolivar, located on the Colombian coast. And in its internal bays, we then did the test on shallow water with a depth of anywhere from 16 to 22 meters. And the ratio for the fluid number for a boat was 0.3. Now, in this navigation condition, we reached a maximum speed of 16 knots. Also, we also ran some tests in the canal, in the back canal, also within the Bay of Cartagena, and we found waves of 2.5 and 3.5 meters. What did we expect to have to obtain in these tests? Well, first, that this peak of resistance, given the shallowness of the water, that we would be able to cover in the moment we did, that this was going to be reflected in an increase in speed of the design speed, which in fact was the case. We reached a speed of 16.5 knots in 3.5 meters, a speed of 16.7 knots in 2.7 meters. And to validate the minimum depth that we found here, we took the boats to the marshes of the Virgin. The depth was 1 meter, and over there we were also able to go above, overcome this resistance peak, and as was expected, we obtained an increase in speed up to 17 knots. And here we can see the predictions of the speed based on the rated power, the propeller as selected, and the resistance that we obtained according to the analysis in CVP. And the speed that we were going to reach was about 16 knots, which shows that the experimental tests were a success and that the simulations were very good. Now, as conclusions, we see that the result of the resistance to the forward movement in shallow waters were completely coherent with the experimental studies and the existing numerical studies, which, as I said, are very scant. The subcritical, critical, and supercritical areas were identified, and the change to the resistance to forward movement in each, right? The critical area being the most important one. And in the supercritical, we obtained a reduction in the resistance to the forward movement, which ultimately led us to a higher speed. And that's the next conclusion. We evidenced an increase in speed and a flew of greater than 1.2 as a consequence of the reduction in resistance. We also verified that the variation of resistance is due to the residual component and not the viscous component. Also, the generation of wave. To be able to tell the crews that they have to be careful when navigating in this regimen, because that is when they Well, first, the resistance is highly effective, and second, the wave generated by the wave, the wake has a lot of energy, and they will generate damages for the riverside population and other smaller boats. The effects of shallow water must be taken into account during the initial design phases, and this applies not only on boats. This relation that I mentioned of length over depth varies based on the ship. What does this mean? Well, it means that even a large size ship, when coming into a canal or when navigating in a depth of 60 meters, that ratio, even though one might think that 60 meters is enough, perhaps for a given boat, it will be an application because it is experimenting these phenomena of shallow water. And last, the validation of the distance of CPD in operational tests, which allows us to validate the power and speed predictions. Lastly, we would like to thank Rear Admiral Oscar Varietas Munoz, Captain Luis Aranivar, Captain Manuel Alejandro Ariza, Ferry Misael Zarate Patarroyo, and Engineer Marta Vázquez Verdugo, and the corporation for the support they gave us this work. All right, Nicolas, thank you for your presentation. If you allow me, I would like to make some comments, which invites us to reflect. You invite us to reflect, you know, when you said that there is a significant contribution to the state of art, given the scarcity of literature on these sorts of experiments. Could you tell us what the most important reference in the literature or the experiment in Colombia or elsewhere in the world was to be able to draw the result that you have presented on? Well, the reference, I believe the most significant, well, we have to make two. Perhaps the articles of Raudip and the author of the University of Michigan. They were the most significant and the ones that helped us most to understand this challenge in particular. I would quote those two articles. Perfect. Now I will convey two questions that we were sent via social media. First, what are the dimensions of the ship that you validated with the results? That is the vessel that you validated with the result. The boat in water has a 7.5 length, beam of 2 and a displacement of 72 displacement, and a draft of 72 centimeters. That is also a great value because simulations, very few simulations can be validated up to actual size. How do you do it? In the model basin, and those results are extrapolated to a ship. Now, we had the fortune of having the results in simulations for an actual size boat, and we were able to do all this campaign or test by validating and then validating the results. And that was a significant contribution to this field of study on the performance of ships in shallow waters. Perfect, Nicholas. Thank you for your presentation. A pretty important piece of work because it has applications not only in naval engineering, but it also generates knowledge for the crews that will be manning those boats, but which is also an important part which will make us rethink the navigational doctrine. Thank you. Thank you very much.
Bueno, tenemos una segunda conferencia.
So we have a second very interesting presentation in this hall. We invite Mauricio Garcia Navarro, also from the Science Technology Corporation for the Development of the Maritime Industry. He is a mechanical engineer with the master's in naval construction, expert in naval construction, fluids and mechanical expert. He's been working as an auxiliary of design in the corporation. His presentation is in numerical study for the hydrodynamic drag coefficient for a current in port assistant maneuvers for the Colombian Navy frigates by means of CFD. Mauricio. Well, thank you very much. Thank you for the introduction. Thank you everyone for those who attend the presentations. I will now then make the presentation. This is a job that we have done with the help of Engineer Luis Leal and Lieutenant Nicolas Ruiz, who just made the previous presentation. Now the presentation has an introduction on the capacity, the environmental conditions of the particular case we will study. What are the equations that are used to estimate the pull weight? Both the analytic and the classic methods. There's the case study in particular, the methodology, that is the description and the calculation of the components, and finally the CFD analysis. And it includes the configuration of the model, the analysis of results, and finally the conclusions. Now, the study came about the need that currently exists in the naval base, ARC Malaga, to have a tugboat that could assist in the berthing and sailing operations. Now, since these boats don't have additional thrusters, this sort of maneuver turns into somewhat complex. So the boiler pull is the match definition to determine the capacity of strength that ship may exert by pulling from a fixed point. Now, generally, during trials, we run a test using a fixed point where the vessel is tied, and then you use a transductor element to record the strength that the vehicle is capable of exerting. This value of that strength is recorded for at least 10 minutes. We take an average of that value, and that is ultimately the capacity that you record with the authorities, right? The tugboat, in the boiler pull condition. And so we move on to the existing environmental conditions, right? The zone is located in the southwest of the country. There is a bay, so it is guarded from the sea waves, but influenced by the tides, right? High tide, low tide, and that generates current in the port. Now, the type of port that we have in this port is a pier, it's an open pier, and it is built on pillars. And these pillars make the current increase the current in this zone, because the current flows below the pier, and that turns it into a faster current. So we held a meeting with the experts to talk about the maneuver, when coming in, and then we collect information on both the depth and depth varies anywhere from 6 to 10 meters, with a maximum speed of current at 8 meters. The zone that you see on the image experiment, less than you get speed winds of 7 to 8 and 12 knots, but at times you have 18 gusts of 18 knots. The most complex operations occurred in point B. Something very particular happens, depending on the location where the ship is berthed. It experiments different types of forces as the effect of the currents. At some point, the ship is attracted to the pier, others is pushed, and obviously those directions of those arrows change depending on the direction of the current as it is produced by the tide. So be mindful that this zone is also influenced by the wind, although moderate, because it is a bay and it is guarded, shielded. Now, if you take into account to estimate the bull wave, the classic, there are some semi-empirical formulas which makes it possible to determine the polar pole value very quickly. However, it considers fairly high safety factors. There are also some tables, which, for instance, that we have at DMAR, that take into account the size of the ship, the characteristics of it, and depending on those values, then there is a table to indicate the number of tugs necessary for the maneuver and the bull capacity that each has. And these capacities are designed for large ships such as tankers or liquefied gas ships, right? Now, the additional manner of calculating tugging calculations for a ship that is to be tugged or pulled is done by dividing each of the forces that act on the ship per component or by component, among them the current, the strength of the wind, and the strength of the waves. Here we see some of the formulas that you find in the D&D manual, where the effect of the current and the effect of the air, which as such are effects produced by a fluid, follow the general drag coefficient formula. Values such as speed and the area, as well as the submerged transversal area, are taken into account. Also, the waves that might exist in the area, considering the significant height of the wave, the speed with respect to the vessel of waves, and the beam of the ship, as well as its draft or depth. For our particular study, we made an emphasis on the Almirante Padilla class, which is a considerable size ship, and for our case, this vessel implied the biggest challenge when engaged in berthing operations in the bay. These are the characteristics of the ship with a considerable displacement. It is a ship that does not require the assistance of a tugboat to perform the maneuver. But it should be said that this study also follows the bibliographical references of Cook as well as Velosim, which deal with, it's an organization that undertakes studies on drag coefficients. In this case, the bibliography, when the bibliography shows results of the drag coefficient for a ship at different angles, with the most critical coefficient being when the vessel stands at 90 degrees. That is when the full effect of the current is received broadside. So it is important to generate that during maneuvers, the tugboat assists in the to help with the heading, and it turns with respect to the geometric center, but it not that it is pulling fully pulling the vessel from one side. It just helps the vessel so that it can either sail off or berth in. So we use approximations of large ships such as the tanker vessels or container ship vessels or liquefied natural gas, as opposed to the hull that we have here of the frigate, the Clase Padilla. But that, we could get different results. So the methodology that we have developed consists, meeting the requirements of the ship that we can use, then compile the local environmental variables, that is the current velocities and directions, wind velocities and directions, the significant height of the wave, the depth of the port, and then consider the most extreme case as the maximum record. For this method, the formula used is that delivered by the Department of Science of the United States in the UCC manual. For purposes of wind, this formula takes into account the Velic area of the vessel as well as the hull as exposed to wind, to estimate the drag coefficient that the wind exerts on the hull, on the ship. That way you can obtain the value of the drag coefficient of the Velic area and determine the strength that the wind exerts on the ship. Similarly, the same reference is used to apply a form also, but in this case, taking into account the effects of the shallowness, of the low drag, both of which are influenced by the effect of a wave, but they are influenced by the low draft, right? We have a drag coefficient basically where we don't have a distance below, but from there on out, and considering the change in depth, you could estimate the transversal drag coefficient on the ship. In this case, given this form, and also some additional coefficients that are also formulated in the bibliography as the cap value, and we get a drag coefficient of 1.29. On this slide, we can also see that big effect that the K values have and the value of the depth on the transversal drag coefficient, and how that force can affect in the end of the calculation by increasing that output, considering the variability of these variables, right? Changing nature of these variables. We also take into effect the force of the inertial forces that occur during the sail off and the berthing, which correspond to the acceleration or de-acceleration of the ship when arriving to port. Now, this force is important considering that it not only includes the inherent inertia of the mass of the ship, but also the added water mass, which is added to the whole and the effect of acceleration. Now, what you see on the slide shows us one of the forms presented by Painthesen on the use of the tugboat in port, where the form already assumes a uniformly accelerated or deaccelerated movement to estimate these values of the inertial force, but adding some additional security factors. It is important to take into account that the maneuver speed at this point in port are of about, well, it's centimeters per minute. So eventually those accelerations might be low, but during emergency cases, they may also be high and must therefore be considered. Of the three forms that I showed you before, the most representative corresponds to the effect of the force exerted by the current on the ship. And taking that aspect into account, that we make use of the CFD tool to estimate a more appropriate, more real drag coefficient based on the whole shape. Right, we do the validation of the CFD working on a scale boat. We had a Reynolds ITTC also is recommended and FD of 0.1. Now the borderline conditions are the same as established previously in the bibliography, as we mentioned, where you have the length to port on port side, starboard and bow and stern and upstream. The borderlines that are imposed on the model are walls without sliding, and at the bottom, two pressure inputs, and then a non-sliding borderline conditions on the hull. Now for the meshing, we used the K epsilon model, and we also incorporated a Y plus of 30 for the limit layer with 10 prisma and a thickness of the first limit, which is 0.04 meters. Notice that as opposed to resistance to forward movement, in this case, we could not use symmetry, and we need to simulate the complete domain. In this case, we applied refinement under the keel in such a way that one can capture the low draft of the effect of that on the boat as well as on the stern and the bow. In this case, we performed 3 simulations where we increased the number of cells incrementally, and then we obtain a drag coefficient value of 1.55 and a number of cells to reach that of 21 million. Here we can see a bit, the example of the result of that, the whole shape, which is somewhat delta shape, but to the side, as we saw previously, it does like a leaf effect or blocking effect of the zone, and it generates some flow lines that eventually affect the drag coefficient. Now, in addition to that, one can see the drop of the restriction of flows under the keel and the increase of speed in the medium zone, gaining greater speed in that zone, and to the side, a more standard speed according to the flow that was configured. Here we can see the comparison between the results as presented by the paper and contrasted without results on the surface, and you see the effect of the pattern of the wave, a very similar pattern, considering that on the stern and bow, you also, well, according to this model, you see, they use higher speeds than our model. Again, same effect, but now considering the effect of the values of the flow zones, again, showing the effect that hole shape has to create certain patterns which could affect the drag coefficient. Over here are the results that similarly show these effects. And then, well, the conclusions. It is important to take into account these analytical methods as presented by the bibliography are not necessarily accurate, and we recommend to make use of tools such as the CFD to estimate these values of the drag coefficient. In our case, by doing a sort of like an inverse relationship in the formulation, we got that for the CYZ effect to obtain the CYZ value of 1.55, we have a K value of 1.9, which is somewhat different to that we saw in the literature, which was 2, but significantly impacting the drag values. And then lastly, I would like to thank Admiral Hall, Captain Aníbal, Captain Elisa, Captain Sarate, Engineer Omar David Basket, Cotegmar, and Odin. My most esteemed Mauricio, thank you very much. Something worth highlighting. These 2 papers that we have just seen are the result of 2 institutional requirements. Requirements from the Navy. On the one side, we saw in the first presentation that there was a need, given the operational conditions of some ports on rivers, and you now have shown as a pretty important paper for the capital ships of the Navy, precisely the frigates. Do you think that this sort of contribution for the force, for the Navy, are important to improve not only the capacity of the engineering office of Cotegmar, but also to improve the operational procedures on board ships? Let's talk about it in terms of operational security. Well, they significantly have an important effect to be able to develop these capabilities, because as we have greater accuracy in these calculations and that data we obtain, that can eventually represent not only a reduction of risk, but also a reduction, an eventual reduction in costs, right? That we may need to develop some other model. It used to be that the formula that were used in engineering, or which, and by the way, they're still valid, sometimes take into account perhaps high security factors, but these tools allow one to get a clearer picture of that, a margin that you can have, the security margins that one, I would say, could have been taken into account and achieve, I repeat, important reductions of risks and or costs. Perfect, Mauricio. Thank you very much. Also, one of your conclusions draws interest. When you say that it is worth going a bit beyond what the analytic method tells us, the traditional methods, right? And I believe that in CFD we find an important tool to go about these sort of validations, and surely we will be able to achieve those levels of optimization. What else can you tell us more about this conclusion? Because I believe it's an important contribution, not only for the field of engineering, but just like we said not minutes ago, to find those margins in terms of operational safety for ship, but more so in the case of the frigate in a navy. Yes, it is important to take into account that the optimization is important. However, it should also be looked upon with care, because eventually, sometimes optimizations, when not performed following a proper criteria, you could then end up on the other side. You could perhaps experience an undesired result. That is why the application of these new optimization methods is it's important. You know, we need to take to contrast, to compare these new methods with the traditional methods, so that we can gain security in our calculations and the results that we deliver. Right, Mauricio, thank you very much. Again, on behalf of the corporation, a pretty important contribution, no doubt. Thank you.
Entonces, sí. 1, 2, 3.
De esta manera hemos terminado la jornada de la tarde con las ponencias técnicas.
So we have come to an end of the afternoon sessions with this presentation. We thank everyone who conducted to this COLOMBIAMAR 2021 7th International Naval Design and Construction Conference. Throughout the following days, you will be sent your certificate of attendance to the email account that were registered during the registration process. Without anything further to add, then we move to the closing remarks of the President of COTECMAR, Admiral Velosa. The floor is yours, Admiral.
Muy buenas tardes para todos.
Good afternoon, everyone. Initially, I would like to extend my thanks to all of those who accompanied us from different parts of the country and the world throughout the live broadcast of COLOMBIAMAR 2021. Through your participation in the 7th International Naval Design and Engineering Congress, which we had to conduct digitally given the pandemic. Likewise, I would especially like to thank all the speakers, the panel members, and of course our chairman for having shared their knowledge in this important academic setting. We cannot talk about design or naval design and engineering without referring to maritime activities. 98% of world trade moved on top of the water. So ports had to maintain their operations throughout the pandemic to ensure the supply chain, and workers and navies had to continue with their mission to secure the sea and also protecting cargo. The emergency generated by COVID-19 has also made us reflect on the importance of self-sufficiency and technological sufficiency. And it is precisely for that we are here today. That is how in settings such as these, it becomes evident, the need becomes evident to bet on the production sectors and local value chains as a relevant aspect of maritime activities, as well as the transformation, the digital transformation in the shipbuilding industry. The challenges and the strategies for the appropriation of new technology, the improvement and efficiency in naval construction processes, unmanned vehicles, and the use of alternate energies, which imply new challenges in terms of naval design and engineering in Latin America. The foregoing commits us as an industry to continue with the commitments we acquired in the agreement for the growth and generation of employment in terms of investment, the chaining of production processes, and the sophistication of our high value-added export supply. Through technological independence that this industry provides to a state. Likewise, we are committed to continue to develop social impact technological offers to provide responses to themes or matters in our country regarding health, education, logistics, and transportation for populations in the farthest reaches of our country that can only be accessed via the river or the sea. Today, we end this 2021 conference with successful presentations, 20 technical presentations, and the participation of over 2,700 people connected both locally and internationally. I am sure that these scientific debates and exchange of knowledge in the frame of an intense academic agenda have strengthened the positions among all the actors in the national and international shipbuilding arena. I avail myself of the opportunity to invite you for COLOMBIAMAR 2023, which is to take place within the activity of the bicentennial of the Colombian Navy. It'll take place in Cartagena, and we hope to continue to strengthen our academic, scientific, and commercial links while we wait for the reactivation, the economic reactivation of the country and of the world. Thank you all.